Coming up on Dr. Kiki's Science Hour, we're talking about hidden universes with scientist and author Dr. Brian Greene. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is Twit. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with me, Dr. Kiki, episode 126, recorded on Thursday, December 15th, 2011. Hidden from View. This episode of Dr. Kiki's Science Hour is brought to you by Ford, featuring available voice-activated sync. Sync gives you versatile access to music, podcasts, and more from just about any device. Check it out in the new 2012 Ford Focus and at Ford.com/technology. And by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Good morning, everyone. It is Dr. Kiki's Science Hour, and I am Dr. Kiki. Today, we are going to be digging into a very special subject for the holidays. Everyone, regardless of who or where you are, you're probably looking forward to gifts, whether they have to do with Hanukkah or Christmas, or maybe it's a special New Year's gift. There's secret, hidden packages that you have to find and dig into. And so today, we're talking about the secrets of hidden universes, worlds that are hidden from our view currently, but the work of theoretical physics and mathematics are showing them to us. And today, in our 1 hour, you know this show, 1 hour digging into a topic with one expert in a particular field. We're digging into this subject with Dr. Brian Greene, scientist and author, professor at the University of Columbia University in New York. Brian Greene received his undergraduate degree from Harvard University in 1984, his doctorate in 1986 from Oxford. He was a Rhodes Scholar there, and he joined Cornell University in 1990. He was appointed to full professor in 1995 and joined Columbia in 1996 as a professor of physics and math. He's the co-founder and director of Columbia's Institute for Strings, Cosmology, and Astroparticle Physics, a research center seeking string theory's implications for theories of cosmology. His first book, The Elegant Universe, which many of you might be familiar with, was finalist for the Pulitzer Prize in General Nonfiction, won Britain's top prize for a book on science, and has sold more than 1 million copies worldwide. His second book, The Fabric of the Cosmos, spent half a year on the New York Times bestseller list and inspired the Washington Post to call him the single best explainer of abstruse concepts in the world today. His latest book, called The Hidden Reality, is a considered exploration of the science of parallel universes. And you might be familiar with his 3-part Nova special that's based on The Elegant Universe, and more recently, a 4-part series that was based on The Fabric of the Cosmos, which aired this fall. With his wife and Emmy Award-winning journalist Tracy Day, Greene is also co-founder of the World Science Festival, which is one of the highlights of the cultural experience in New York City. Dr. Greene, thank you so much for joining me on the Science Hour this morning.
Oh, it's my pleasure.
It's great to have you. So let's get down to it. Hidden Realities is your book that you've published this year on parallel universes. What led to the writing of this book?
Well, a number of things, but foremost is a series of developments in fundamental physics, which are purely mathematical at the moment. But when we follow the mathematical equations, they are suggesting to us that our universe might not be the only universe. And we have learned over roughly the last 50, you can even say 100 years, that mathematics has the ability to reveal aspects of reality that we haven't yet been able to directly observe or directly experiment with. We thereby are willing to take certain mathematical ideas seriously and see where they take us. So what this book is, it's a compendium in some sense of the recent reasons why physics is considering other universes, as well as some allied reasons why, since roughly the 1950s, there's been reason to consider other universes. And the book is really a critical assessment of these ideas. It's not a cheerleading book that's trying to say, here it is, the new idea of parallel worlds. It's saying, here are the ideas, here's why we take them seriously, here are their weaknesses, here's how one day we might be able to test these theories and know whether they're right or wrong.
In comparing this book to the other books that you've written, was this subject a little bit more difficult to dig into, since it is such a really purely mathematical concept at this point? Well,
The Elegant Universe, which was an exposition of string theory and the theories that led up to string theory, namely general relativity and quantum mechanics, it too is based solely in mathematics. We have no direct evidence, or even some would say no evidence at all, that string theory is correct, because it describes realms of the universe that are very, very difficult for us to test, to experiment with. So that book, too, had the challenge of communicating ideas which emerge from mathematical investigations and trying to make them vivid, trying to make them something that one can picture in the mind's eye, something that comes to life and is not just a bunch of technical symbols on a page.
Right.
So, in a sense, that book gave me experience with trying to translate things that emerge from math and make them available to those with no math training. So in that sense, this latest book, The Hidden Reality, follows the exact same pattern. The main difference, I would say, with The Hidden Reality is it doesn't tell a single story. In The Elegant Universe, there's a very singular story of basically Einstein had this dream of a unified theory, and then I walk through his dream, how it didn't get realized in his lifetime, and what we've done since to try to find the unified theory. So it's a very narrative-driven story that ultimately speaks to the goals of the greatest scientists of the 20th century. This book, it doesn't have that kind of singular thread, because my goal was not just to tell one line of development that gives rise to parallel universes. That could be interesting, but my view is what makes the subject particularly compelling is that there are independent lines of research in quantum physics, in cosmology, in string theory, and allied fields that come upon their own version that our universe is one of many. And it's the convergence of all of these different lines of research that, to me, is particularly exciting. And that's why this book tells many stories, not just one.
Yeah, in the sense of the convergent aspect, do you look at it some way there's convergent evolution of traits? Different animals have similar solutions to a problem, but they come from different sources, different environmental pressures. Do you think that there's some kind of a parallel there in this convergent development of the idea of parallel universes by these different disciplines?
It's hard for me to see what that would be, although I like the idea. It's a little hard for me to see how it would play out, simply because the main difference between the biological example is many of the similar traits, or the similar problems is perhaps a better way of saying it, that different organisms face come because they all share the same environment, and thereby are presented with similar problems, and some solve it one way, some solve it another, and those that don't solve it, well, they don't carry on, so we don't really know about them.
Right.
The developments that I'm referring to don't really come from immersion in a communal environment. They really come, and this is what I find particularly striking, from scientists that are trying to solve very different problems that don't really have a connection with one another. In quantum physics, for instance, back in the 1950s, a gentleman named Hugh Everett from Princeton was trying to solve a problem that's actually still with us today. I just came from a conference in Arizona that was focused in part on this problem, which is that in quantum mechanics, the math tells us that you can only predict the probability of getting one or another outcome, which is a very non-Newtonian idea. Newton's view was, tell me how things are today, I'll use my math, and I'll tell you how they will be with certainty tomorrow. If you give me certain initial conditions, I will give you certain outcomes. Quantum mechanics is very different in that regard. Regardless of how good your input is, the best it can provide as output are likelihoods. So an interesting question is, if, say, an electron can be here or there with a certain amount of probability to be here, 30% here, 70% there, when you actually do the experiment, you always find it in one or the other location. So if you find it here, the question is, what happened to the possibility that it could have been there? Now, some would say, well, it just kind of evaporates into thin air, but that's hard to square with the math. So Everett came up with this idea that what actually happens is, when you do the experiment and find it here, there's another version of you that also does the experiment and finds it there. Both outcomes happen. They just happen in parallel worlds, parallel universes. As crazy as that idea might sound, from the math standpoint, it is the most economical, the most conventional, the most straightforward interpretation of the fundamental equation called the Schrodinger equation of quantum mechanics. So he was trying to solve that problem and came upon this idea of parallel worlds. Other physicists trying to solve other problems in cosmology, for instance, we can talk about that if you're interested, also came up to this idea of parallel worlds. Completely different consideration. Do you want to hear how that one went?
Absolutely.
So we, for a long time, we've been talking about the origin of our universe in terms of the Big Bang Theory. And that idea, I think, is familiar to most people. The idea is a long time ago, our universe, everything we see around us, was squashed to a very, very tiny size, ultra-dense nugget that underwent this rapid swelling, this rapid expansion, giving rise to the universe that we see around us. Now, we have been trying to understand that process better and better over the decades. And in the 1980s, Alan Guth, who at that time, I think was at Stanford, was working with another fellow, Henry Tye, at Cornell. And the bottom line is, they came to the conclusion that the Big Bang might not have been a one-time event. Their work gave rise to some understanding of what might have fueled the outward swelling, and in the hands of other scientists like Andre Linde and Alex Vilenkin, it became clear that there's no reason to expect this outward swelling to have only happened once. There could be many Big Bangs giving rise to many different universes. These considerations are very different from the ones that were driving Hugh Everett in quantum mechanics, and yet a flavor, a version, a variety of parallel worlds emerged from that research too.
In the sense of these events happening multiple times, the quantum mechanics example, you have, say, for example, in photosynthesis, there's evidence now that that electrons, that photons of light hit the photosynthesis machinery and take a quantum pathway, looking for the most efficient route through the molecular equipment to get to the other side to create, go from light to electrons, creating energy. What happens to all of the pathways? And if you consider it on the scale of each one of those pathways that the photon takes, is each one of those possible pathways taking place in a parallel reality? Is there such an immensity to the number of parallel worlds that are possibly out there?
Yes, it is a very strange idea to envision, not only in the interesting case that you are referring to, which I've only just started to read about myself. It's fascinating, this whole idea of, quantum biology, quantum photosynthesis. First, when physicists who don't know about it all encounter this idea, it sounds kind of like the stuff that we receive crackpot mail, and when people have these ideas of how quantum mechanics, affects everything that we see around us in some very flat-footed way. But serious people are looking at these ideas and finding that they may well hold water, so it's very exciting. But back to your question, yes, indeed, if the way in which a quantum system can evolve has many pathways, it can evolve this way or that way or the other, then in this Everettian approach to quantum mechanics, one does actually envision that all of those pathways are realized. They're realized in parallel, in a sense, and indeed that suggests an enormous reality. The landscape of reality would be mind-bogglingly huge from the perspective of the ways in which we like to speak in terms of a planet and a star and a universe. You'd have many of these things happening in some sense in parallel. The point that I would stress is that however uneconomical, however excessive that may sound, it's not the right measure to use to judge whether this proposal is sensible. Because if you look at the equations, and this is sort of the main point, if you look at the equations that are underlying this excessive reality that seems to be emerging, the equations are as simple as they can possibly be. So other approaches to quantum mechanics, which deny that all of these parallel worlds are out there, they're viable, and it's really up in the air as to which is the right approach to take. But a number of the other approaches, even though they don't seem as excessive because they do yield, say, one reality, that feels good, it makes our hearts stop palpitating.
It's
even
discrete.
Though it yields
My mind can handle it, yeah.
Exactly. Even though that is what emerges, the underlying equations in some of those proposals are more complicated than the equations underlying this many worlds approach, which is just to say you have to be careful when judging an idea in terms of how complex it is, because what's the right yardstick? Yeah. Even if you take Darwinian evolution, you look at the world outside and you recognize there are a lot of different life forms. There are a lot of different kinds of insects. And from the perspective of the variety of life, it's hugely uneconomical in the terminology that I was using before. It's not that I don't love the richness, but there's a lot of different kinds of life out there.
And is it really
however,
necessary,
comes from a very simple idea.
Right. Yeah.
So the idea is simple, the outcome can be complicated. And that is what would happen in this many worlds, many universe approach to quantum mechanics. Now, in the book, I should stress, I have a whole chapter, and this is one of the stories that I tell in terms of the development of this quantum mechanical many worlds approach. And, I had friends of mine read the book as I was writing it just so I would get a sense of, are they getting it, non-technically trained folks who are friends of mine. And, a number of them, when they read that chapter, they said, yes, I get it completely, and you're so even-handed, and you're so willing to expose the issues that I've concluded that the many worlds approach doesn't work. And that's a fine reaction, because there are some serious problems, in my view, with the many worlds approach. But yet the ideas are sufficiently compelling, and researchers are working on it today who think they've solved those problems, that it's spectacularly exciting to learn about this approach, which may, who knows, be right.
When you look at the landscape of researchers involved in studying parallel universes, in developing this area of theoretical physics, how does it compare to string theory? String theory has been worked out for years, and it seems like it's a very there's still controversy as to whether or not it's going to be the unifying theory, and we're hoping that the Higgs and the LHC are going to give some evidence towards that. But in terms of the problems, how does the parallel universes idea pan out?
Well, the developments in string theory do provide another pathway, a somewhat independent pathway to this idea of parallel universes. Yeah. And it's really, in some sense, the reason why I did write this book was these recent developments, which I find both exciting, but I'm very skeptical at the same time. And that's an interesting combination that doesn't always come across if I'm doing a shorter interview, not one like this where one has the latitude to give some nuance.
Right.
You know, in shorter interviews where you're just talking about the ideas, and yes, I am excited about the ideas, it comes across sometimes as I am definitely certain that this parallel world approach to string theory is correct, and nothing could be further from the truth. As again, the book, of course, has the ability to explain because one can obviously go into much more detail in that setup. Yeah. But it is a fantastically interesting development, and it basically goes like this. Let me just tell it from a personal perspective. You know, back in the 1980s, I was a graduate student at Oxford. And that was when string theory was really just grabbing the attention of physicists around the world. And my particular interest in string theory came from the fact that it required more dimensions of space than the ones that we know about. We all know about left, right, back, forth, and up, down. But the math of string theory required additional dimensions. And that just struck me as wondrous and weird, and I wanted to investigate it. So we did, as did many others, investigate this idea of extra dimensions. And in particular, you know, my thesis, my doctoral dissertation, was taking one particular shape for the extra dimensions. These dimensions are thought to be very small, crumpled up to a very small size, too small for us to see with the naked eye, but nevertheless all around us. And I took, with a couple of graduate student friends of mine, we took one potential shape for the extra dimensions and worked out what physics it would give rise to in the everyday world, because these extra dimensions affect things like the mass of particles and the strength of forces. And so we did this calculation, and the results did not match what we see in the world around us, but we were like, well, this is just the first attempt. Let's go to the next shape. At that time, there were only like 5 known shapes, so it seemed you might exhaust all of them and figure out if one gives rise to physics we know and love, fantastic. If they all fail, well, then maybe you kind of rule out the idea. The problem is that was in the mid-'80s. As the years went by, mathematicians and physicists found more and more candidate shapes for the extra dimensions. Thousands of more, millions of more candidate shapes. If you had a catalog of these shapes, the number of pages just started growing voluminously. Until today, the number of candidate shapes has mushroomed to on the order of 10 to the 500 possible shapes for the extra dimensions. Now, the problem with that is, and which has been discouraging for some physicists, only one of those shapes presumably would be the quote-unquote right one, in that it would give rise to the physical features that we know about in the world around us, the mass of the electron, the mass of the quarks, and so forth. But how can you possibly find that shape in a list that's 10 to the 500 entries long?
Yeah,
and
needle in a haystack problem.
Needle in a haystack. So some string theorists saw this and said, I'm quitting the field. We're never going to be able to make any predictions that we can test because we don't know which is the right shape. And that is, in my mind, a completely respectable and sensible reaction. My own reaction for a while was, look, these are deep questions. We've been working on this, sure, a few decades, but we just need to keep going, and we will one day find a mathematical equation that tells us which is the right shape. It will pick out the needle in the haystack for us. We don't need to look for it in that conventional just going through the list. Now, we've not yet found that equation. The third and most radical reaction, which is what really the book focuses on in its second part, some have said, look, let's take seriously all of these different shapes for the extra dimensions. The reaction is, if we've not been able to pick out the shape from this list, maybe they're all real in the sense that there isn't one unique universe. There may be many universes, each having a different shape for the extra dimensions, and our universe is simply that location within this vast landscape where the extra dimensions have just the right shape to give rise to the things that we are familiar with. Electrons that have their properties, atoms that have their properties, that can come together and form stars and planets and people.
Is this something similar to the anthropic principle?
This is basically the anthropic principle, but I'm always reluctant to use that terminology because it means different things to different people, and it makes some people's skin crawl to hear that term. Because some people think of the anthropic idea, which is in a nutshell saying, we are here and things are the way they are because if they were any different, we couldn't exist. We couldn't survive.
It's a just so kind of story.
It feels like a just so explanation. And indeed, if there was only one universe, the anthropic ideas would certainly be a just so explanation. We would simply be saying things are the way they are here because had they been different, we wouldn't have been here to notice. That is completely unconvincing. But if there are many universes, these anthropic ideas are not just so stories any longer. Think about it. If there truly are many, many universes out there with different properties, then of course we're going to be in that universe where our particular properties can exist. How could it be otherwise? And in that setup, it's no longer a just so story because we're literally saying it's not that there are hypothetical other properties that could have been. We're saying those hypothetical properties are realized. They're out there. And of course we can't be where the properties are different because we couldn't survive there. I mean, an analogy which I think helps a lot is think instead of universes, think of planets. You can say to yourself the following, Kepler in the 1500s was worried about understanding why is the Earth 93 million miles from the sun. He was really obsessed with finding a law of nature that would dictate the Earth-Sun distance. Now, that was a fool's errand. Not that he was a fool, he's a genius, but in retrospect, we recognize there are many, many planets. In our solar system, there are many planets out there orbiting other stars. The bottom line is planets can be at a huge range of different distances from their host star. There is no fundamental reason why we are 93 million miles from the sun. It's part of just the historical way that our particular solar system evolved from the dust cloud that was circling around billions of years ago. Now, going one step further, if you say to yourself, so why are we on Earth? Well, that's pretty clear. We couldn't survive on Mercury, too hot. No liquid water. Life wouldn't evolve. Why aren't we on Neptune? Too cold. No liquid water. Again, unlikely, certainly for our form of life to evolve. We are on that planet which has the right temperature for liquid water to exist and other features so that our form of life can evolve. We're here and not on Neptune because we couldn't have evolved on Neptune. End of story. That's the answer to Kepler's question. Similarly, it could be, why are we in a universe with the particular properties that we see in the world around us? Well, there are other universes out there, like other planets. They've got different properties, and of course we're not there. We're not there for the same reason we're not on Neptune or Mercury. Our form of life couldn't survive there.
Yeah, I remember there was something that I read out of the archive.org repository. It was a paper on the idea that even our universe isn't absolutely the best tuned that it could be for life. That there's actually, because it's expanding and that because of certain, I don't remember what number or parameter wasn't as efficient as it could be, but that even though we're here, it could be better. Was the take-home message.
That's a very important and interesting line of research, which asks the question, okay, certainly if features were radically different from the ones that we know about here, then it's hard to imagine our form of life existing. But what if the features were just somewhat different? Could life exist? And as you're saying, could it even be easier for life to exist? Just like, we're on the Earth, but there's certainly, you can envision other Earth-like planets that might be even more conducive to life as we know it, as opposed to what we're familiar with here on Earth. And those are interesting questions, and those are definitely worthy of study to try to flesh out this picture. The point that I would want to underscore is this possibility of other universes naturally emerges from the math of string theory. It gives rise to this interesting picture of why we're here and not somewhere else, but that doesn't mean it's right, And frankly, if you were to ask me, do I believe this picture, my answer to you would be a flat-out no. Now, I don't mean flat-out no in the sense of I think it's wrong.
Right.
It's a no in the sense of I don't believe things until there's proof, in the sense of experimental or observational data that gives me some confidence that these ideas are actually relevant to the real world as opposed to just to mathematics. So I'm very much on the fence about these ideas. I'm not as I was saying before, a cheerleader for other universes, but man, I find the idea exciting, and it's definitely worthy of investigation. And the point of my book is to allow the general reader to get a sense of where we're at in this investigation of other universes and what we need to do in order for this line of inquiry to come to a conclusion as to whether it's right or wrong.
All right. I need to take a quick break for a message from our sponsor. And everyone, I hope we will dig into this question of what needs to happen in this line of research when we come back. So why are you here? Why am I here? Well, because this show is sponsored by Ford, featuring available Sync. Sync's entertainment features enable you to access music and podcasts from most devices, including your iPod, your mobile phone, tablets, or even flash drives. And with Sync with Myford Touch, you can play videos or display photos from your digital camera or portable game device when your vehicle is in park. Not while you're driving. We like to keep the distractions away while you're driving. It's all made possible through a versatile media hub, which supports a convenient variety of devices for your music and entertainment, such as wired connections from just about any device through USB ports, SD slots, and RCA jacks, or wireless access through Bluetooth from Bluetooth-enabled devices. Just connect your devices and play. Once your device is connected, you can use Sync's voice activation feature to play what you want. Just a few of the simple voice commands are play genre. Choose something like rock or jazz or reggae, whatever your favorite is. Play artist. Play track. So I could say play Adele. Play whatever song I'd like to hear. Also available is Sync with Myford Touch HD Radio. This features iTunes tagging, which lets you tag a song you like on the radio, transfer the information to your iPod, and then purchase the song directly from iTunes at a later time. Sync's versatile entertainment features are available in the 2012 Ford Focus. You can learn more about this and other technologies Ford is bringing to vehicles at ford.com/technology. I'm speaking now with Dr. Brian Greene. We're talking about his recent book, The Hidden Reality, that's out this year, available. You can find it a whole bunch of different places, Amazon.com, other book-selling places, wherever you like to purchase your reading material. And we were talking about the idea of these parallel universes, and before the break, how they come out of string theory. Specifically, Dr. Greene, you mentioned that it's not a fully developed field yet, that there's still a lot of questions, and while it's intriguing academically and maybe even in a cultural sense to find out what are we a part of? What is our universe one among many? Now that we know our world is one among many possible Earths that are out there. What are some of the challenges to developing this idea further? Where is it kind of at the moment?
Well, it depends on which of the parallel universe, multiverse ideas one is speaking of.
Right.
The oldest one was the one that we started with, the one that comes from quantum physics.
Yeah.
And the challenges that one faces are particularly interesting. There isn't anyone who really challenges that quantum mechanics is a correct theory for describing a whole range of processes in nature, the properties of electrons and quarks and atoms and the way they combine. Ultimately, these are all quantum mechanical processes, and quantum mechanics has made predictions that have been borne out to great accuracy. So everybody believes that this is the right theory. That's not where the question comes from.
Right.
The question comes from this issue that we raised before, which is, since it frames its predictions in terms of a range of possible outcomes, and it tells you the likelihood of getting one outcome or another. The challenge is to explain, A, why it is when you make a measurement, if there are many possibilities, why do you only find one outcome of the many? That's a challenge for the theory to address. And B, give some sense of what happens to the other possibilities when you only do find one of the many. Now, the many worlds approach, getting now to the question, which would say that there are these other universes out there, the particular challenge it has faced has been to really come up with a coherent means by which the different universes would be assigned different probabilities. That's kind of a hard thing to do, because if you're really saying that all of these universes actually happen, in what sense can one of those universes be more probable than another if they're both happening? If they're both happening with 100% certainty.
Right.
And that seems to undermine the whole probabilistic framework of quantum mechanics that wants to provide insight into the likelihood of one or another thing happening. Now, a group of researchers, many researchers have tackled this problem. One group at Oxford is famous for their work on this, and they believe they've solved this problem. They believe they have an answer. It's too technical to describe, but I would say that not everyone agrees that they have solved it. It's controversial. So that really is the issue that needs to be resolved there, to figure out, A, whether their proposal really works, and B, whether it is convincing enough to gain a kind of consensus in the quantum mechanics community that this is the right way of thinking about quantum physics. And that may happen in short order, it may not. I don't know the time scale. If everyone were ultimately to be convinced that the many worlds approach is really what happens, that would be pretty stunning. It would be a pretty wondrous outcome. I don't know if that will ever happen, but that's what needs to happen there.
Right, or whether it'll happen within our lifetimes, right? The quantum mechanics approach to it is also one of the challenge, going with trying to find that unifying theory. You bring kind of string theory into it, or the idea that, so we have these quantum effects that are occurring at a probabilistic scale, and yet we live in this very macro environment. And so you have to tie all of these events together at the quantum level to have what's happening at the macroscopic level actually occur. Yet we still do not have that theory. Do we still need to find
that's right.
Do we need to find it to really understand this?
Yes, I would say it a little bit differently. So even without a unified theory, even without string theory, just pure quantum mechanics, there still is a challenge to really understand in precise terms, how does the familiar classical world that you and I navigate every moment of our lives, how does that familiar, solid, definite world, that certain world, emerge from a framework which says that at the micro level, things are uncertain, that things are indefinite, that things are kind of fuzzy, that things are probabilistic? How do you migrate from the probabilistic realm of the small to the apparently certain world of the big?
Yeah.
And this is a challenge that quantum mechanics has faced from day one. People like Niels Bohr, for whom we give credit really for developing this theory, a leader in the development of this theory in the early part of the 20th century, had his own proposals for how to bridge the gap between the probabilistic world of the small and the certain world of the big. Most people don't fully buy his proposals any longer. They were good for the time. They helped research make progress.
Yeah.
But we need more sophisticated ideas, and people have developed a whole slew of them. And they don't have anything to do with string theory or unified theories per se. They have to do with really trying to understand quantum mechanics better. And as I was just saying, I just came from a conference at Arizona State where it was two full days of 20 people in a room debating, discussing, arguing about the various approaches to trying to bridge that gap. And, I sat there and it was kind of a funny experience because it's the year 2011. These ideas were first put on the table, you could say, in 1905, roughly, where Einstein wrote what many view as the first paper on quantum mechanics, but call it 100 years.
Yeah.
100 years after this theory was first put forward, and roughly, 80 years after this theory started making the most spectacularly accurate predictions science has ever known, we're still locked in rooms trying to fully understand what this theory says about reality. And that's quite striking. Now, from the string theory perspective, though, the question that you asked before this one should be addressed there too. What needs to happen, for us to have confidence or rule out this possibility of the string theory version of many universes? And there the situation is quite different from quantum mechanics, because in quantum mechanics, as I said, we believe the theory in as much as we understand it. String theory, no, we don't believe the theory in as much as we have it yet, because it's not yet made predictions that we can test. So there's a double level of uncertainty when it comes to string theory. What we need to do is understand the theory better, hopefully be able to make predictions of some sort that give us confidence or rule out that the framework is the right way to go. And then as we understand the theory better, we hopefully will understand the specifics of these other universes, the other shapes for the extra dimensions better. Maybe we can say, the vast majority of the universes will have this or that property. And then if our universe happens to have that property, we would say, oh, that's interesting. That feels like confirmation that the vast universes have that property and we have the property. So those are the kinds of things that need to happen. So it's a lot of mathematical development, but ultimately, if the Large Hadron Collider could give us some indication, maybe that there are extra dimensions, one of the hallmark features of string theory, that's something that could emerge from data at the Large Hadron Collider, that would be thrilling. It would definitely push this research forward in a big way.
Is the Higgs boson related to that search at all?
It is, in the sense that one of the prime chapters in our quest to understand the universe at a deep level has been to figure out the basic particles and the basic interactions that those particles undergo to yield the world that we know. And the Higgs particle is the last piece of the so-called standard model of particle physics that had yet to be tested, or I should say has yet to be tested. The data still is quite uncertain. And if we can confirm that the Higgs particle is real, it will complete that chapter. We'll think at least at the level down to roughly 10 to the minus 18 meters or so. We understand what the particles are, and we understand how they get mass, and we understand their basic interactions, and that would be a huge thing for that chapter to draw to a close. None of us are convinced yet that the data from the Large Hadron Collider has done that, but I think many of us are very excited by the recent announcement. At least it gives a tentative indication that the Higgs particle may be real, which is so thrilling at some level because, again, it's a wholly mathematical construct that makes a prediction that this particle should be out there, and then if they actually find the particle, that is just dazzling, that you do these calculations and then it's really out there. And again, look, I have no vested interest per se. These ideas of Higgs were developed before I was born. But it's just so thrilling to see recapitulated again the power of math to describe reality, if indeed these results hold up. So by next summer, we should know for sure. So that would be great if the Higgs is found. But then the next step that we would be looking for would be for other kinds of particles to be produced at the Large Hadron Collider, so-called supersymmetric particles, one of the other kind of particle that naturally emerges from string theory, maybe some so-called missing energy signatures where some debris from collisions may get ejected out of our dimensions and into the others if the others are really there. That would be an indirect signature that extra dimensions are real. Perhaps even the production of little tiny microscopic black holes, huge long shot. But if these little black holes were produced, again, it would be a natural thing to explain within string theory. So all of these developments could give us some circumstantial evidence that ideas that we've been developing for decades are going in the right direction.
And from these ideas, if you get these pieces of circumstantial evidence, will that help string theory make testable predictions at that point?
You hope so. The challenge for string theory is, I think many of us believe that we're probably missing some key idea, probably missing some key element that will give us more of a roadmap from the math to kinds of things that we should be able to experiment or observe. And I think that's probably one of the hurdles that will need to be surmounted in order to really test these ideas. The other thing is not even string theory centric per se. Any theory that purports to put gravity and quantum mechanics together, well, that theory is going to be very hard to test because for it to be viable, it's got to embrace physics that's already been tested, the physics that is taking place now at the Large Hadron Collider, physics that gives rise to the Big Bang and things of that sort. These theories thereby are embracing things that have already been tested. So you ask yourself, where then are they distinctive? Where do they flex their muscles in a way where you can definitely say, aha, there's evidence for that new theory, that new idea. And where these theories flex their muscles is typically in realms that are extraordinarily tiny or extraordinarily massive. And it's very hard to access those realms. The basic place in which string theory would really come to life, at least in its most conventional formulation, is billions and billions of times smaller than the length scales to which the Large Hadron Collider can probe. That is very, very hard to test, anything that comes to life in such an extreme realm. Now, we may get lucky. The Large Hadron Collider may be able to even excite certain string vibrations if the strings are bigger than the conventional approach would suggest that they are. Or these missing energy signatures might happen. Or, finding these supersymmetric particles. All of this will help build a case for these ideas. But it is a huge challenge when theory takes such a leap beyond what we can directly access to know whether the theory is right.
Yeah. I need to take another break for a word from another sponsor. This episode of Dr. Kiki Science Hour is brought to you by Netflix. Netflix streams thousands of TV episodes and movies directly to you instantly, which means you save time, money, and hassle. There are several easy ways to instantly access streaming movies and TV shows with Netflix. You can watch Netflix movies and shows on your Mac or PC or iPad. You can even watch on your iPhone and some Android phones as well. If you have a gaming console like an Xbox 360 or a PS3 or Nintendo Wii, you can watch Netflix right on your television. And if you're not a gamer, you can use one of the set-top boxes that are pretty inexpensive and easy to use, like a Roku box or Apple TV. With Netflix, you can watch movies and TV shows instantly using any of these devices, and you can start watching a movie or show on one device and then finish on a completely different device. Whichever way you choose to access Netflix, you can watch as many movies and TV shows as you want, anytime you want, and you can cancel at any time. Try Netflix today for 30 days free. Go to netflix.com/twit. Be sure to use this URL when you sign up for your free trial. It's netflix.com/twit. We thank Netflix for their support of Twit and Dr. Kiki Science Hour, and we hope that you enjoy watching instantly with Netflix. So we're coming to the end of our hour together, and I wanted to ask you a little bit more about the process of your writing. At the beginning of the hour, you talked about the challenge and I guess I would imagine it would be kind of fun of taking these math concepts that really haven't been described in a popular way before and turning them into a visual concept or a visual concept that you can describe verbally or an analogy of some sort. What's your process to actually approach this undescribed math in such an easy to understand way?
Well, my approach actually is not divorced from the way I do physics itself. So whenever I'm involved in a research project, typically they are all completely rooted in mathematics. And I never feel comfortable if I'm just following the equations as if my full understanding is only supported by the mathematical symbols. I always feel the urge, the need to build some kind of mental image of what it is that the mathematics is describing. So I always am going through this very same process of building up, in some sense, a library of mental images, visualizations of abstract mathematical ideas. I think many of my colleagues, many physicists do the same thing. And then for me, when it comes to writing a book, what I do is I rely on that library of images. I then, of course, strip away all the math because it's meant to be accessible to someone without math training. And then the challenge is to take those images and create some kind of coherent narratives, coherent story, dress them up with some kind of story, dress them up with some kind of analogy that makes use of the visual imagery to try to yield an accessible portrait of these abstract ideas. And, some subjects are easier to do, some are harder. When I was writing The Elegant Universe, I wrote the quantum mechanics chapter last because I was intimidated by trying to describe quantum mechanics in non-technical terms. In the end, the quantum mechanics chapter of The Elegant Universe is my favorite. So, I think it fell together well in terms of the visuals and the metaphors. But, there are definitely other areas of various of my books where, I have to work hard and come up with an idea for describing it, throw it away, try again if I didn't think it was working, and so on. So it is very much a process of tuning and fine-tuning and trying to find the way to take the person from the familiar to the unfamiliar in a way that feels comfortable.
You had a cameo in the show The Big Bang Theory, and in that cameo, Sheldon Cooper kind of mocks an analogy of yours to describe that you use to describe the uncertainty principle. So there are two things about this about that clip that I thought were interesting. The fact that, number one, is the science community's response to the way that you describe these scientific concepts. And then, how did you feel about doing that scene?
Well, in terms of the scientific community, when I use metaphors, especially in the books, one always has to recognize that metaphors always will fail. They never can be fully true to the scientific idea. And the question is to find those metaphors which capture the heart of the idea. And I think I do a pretty good job at that. But the other thing is I often will then say to the reader, and here's where the metaphor doesn't quite work, to try to prevent the person from going down a chain of reasoning that might be motivated by a part of the metaphor that really is not speaking to the core idea. It may have helped with the general approach to a complex subject, but it can't be taken any further or it'll lead you astray. So I try to make some qualifications about these metaphors when it seems worthy of doing that. It's much harder to do that on television. In fact, it's impossible to do that on television. So in my series, even the later one, The Fabric of the Cosmos, an effort, of course, is always made to keep it as close to the science as possible. But again, here the metaphors are standing by themselves because you can't have a footnote, you can't have a qualifying remark because then someone changes the channel and goes to watch, Dancing with the Stars or something. So it's harder in the television domain, but the books at least you have the ability to explain things out in a way that really works. As far as the television show, it was fun to do, and I was warned up front that Sheldon has to insult everybody that he comes in contact with. Apparently, I don't really watch the show in detail. So I was perfectly fine being the foil because in the end of the day, it was just for a good purpose of getting these ideas out there. So I didn't mind taking one for the community in that sense.
I think it's a worthy cause, getting out and putting that face on science. You also do a lot of work beyond the books that you've written and the TV series that you've done in getting science out to the public. You started the World Science Festival. Is there anything that you're particularly looking forward to with the World Science Festival in 2012?
Well, there is one thing. You may be familiar that I wrote a kid's book called Icarus at the Edge of Time, about a boy. Icarus doesn't go to the sun, but he flies a ship to a black hole against his father's advice, and then the physics of general relativity dictates how the story unfolds from that point. And we turn this into a live stage presentation with a score by Philip Glass, and a narrator reads the story in a Peter and the Wolf story, type of presentation. We have a film by Al and Al, two artists from the UK. And we did this once in New York back, I think, in 2009, and we're bringing it back for the 2012 festival. We're going to be doing it in New York for a large audience that we hope will be largely kids and families, that will allow them to sort of get excited about a piece of physics, general relativity, by virtue of sort of participating in this staged story. So I'm excited that we're going to be doing that again.
That sounds really exciting. I'm looking forward to the World Science Festival coming up. There's always just the bringing together of art, culture, science over a week is truly inspiring, and the team that you have producing the event seems to get the best communicators of science that it possibly can. So it makes for a really fun event. I will not keep you any longer. We've had our hour, and I truly appreciate your time today, Dr. Greene. Thank you so much for joining me.
I enjoyed
Have a
it.
great
Thank
day.
you.
Thank you very much. Bye. Many thanks to Dr. Brian Greene for joining us here on Dr. Kiki's Science Hour, and for all the information about the hidden universes around us. Who knows? They might be out there. Read the book, find out where they're hiding. Be sure to visit briangreene.org for more information. I'm Dr. Kiki, and this has been the Dr. Kiki Science Hour. Be sure to watch again next week, when we will have another hour with another expert on another subject in the sciences. Remember, this is what I try to do, bring the science to you. Until then, you can follow my sciencey pursuits on Twitter. I'm at Dr. Kiki. My website is drkiki.tv. My Facebook fan page is Dr. Kiki. And you can subscribe to this show in iTunes, or find past episodes if you go to twit.tv/Kiki. Also, if you need more sciencey goodness, I do a couple of other shows. This Week in Science, which airs live weekly on the Twit Network at 7:30 p.m. Pacific time. You can find that at twist.org. Also, you can download episodes in iTunes. And I do my science chat every Friday at noon Pacific time over on Justin TV/Dr. Kiki. You can email me, Dr. Kiki at drkiki.tv, if you have any questions, comments, suggestions for interviews. I think that's it. So I will see you next week. Thanks for tuning into my Science Hour. All I ask is 1 hour a week. And remember, 1 hour a week makes your world a whole lot more interesting. Now, happy holidays. That's right. Happy holidays and Happy New Year to one and all. Now for your science meditation of the week.
Sir Isaac Newton was an English physicist and mathematician, well renowned for his expertise in astronomy, natural philosophy, alchemy, and theology. Much of classical mechanics, or the set of physical laws describing the motion of bodies under force, are laid out in Newton's Mathematical Principles of Natural Philosophy, published in 1687. Newton's 3 laws of motion are perhaps the most well-known of his works, and cite the following. The first law, or the law of inertia, states that an object at rest will remain at rest, and an object in motion will remain in motion, unless acted upon by an unbalanced force. The second law states that acceleration is produced when an external force acts on a mass. Newton's third law of motion states that for every action there is an equal and opposite reaction. Newton invented the first reflecting telescope and devised a theory of colour. The theory was based on the observation that a prism breaks down white light into many visible colours. Newton is attributed with the development of differential and integral calculus, as well as the generalized binomial theorem. He also developed a method for approximating the roots of a mathematical function. A highly religious man, much of Newton's writings consist of biblical and occult studies. Sir Isaac Newton is considered by many to have one of the greatest scientific minds in our history, and he is buried in Westminster Abbey.
Remind everyone that December 25th is Isaac Newton's birthday. So along with those celebrating the I guess birthday of Mithras or Jesus or whomever, Santa, whatever you like to call your December 25th, you can also consider it Isaac Newton's birthday. And so those presents under the tree might be an apple tree, and those might be Newton's birthday gift.